Right, so this is actually not so difficult. If you now go back to the first page, page 10. Page 10 is your summary of everything that you need to know with work, energy, and power. And we've been through it all. It's not that difficult, is it right? Now we're adding momentum to the mix. Now what we like to do is, if you look at the opposite page on page 15, we're going to do this question soon. And this type of question is where they tell you things like James Bond starts from rest and skis down 25-meter slope with a villain at his heels. The slope makes an angle of 38-degree angle with the ground. He experiences a frictional force of 10 newtons. Then at the bottom he covers a horizontal plane for 15 seconds, experiences a 50 newton frictional force. It brings him to a parcel, 1 kilogram fixed to an inelastic rope. He grabs the parcel, he swings up, so they've got a collision with the parcel. He's swinging up, and he swings up and breaks the window, escapes through the door. Okay. And immediately feel, oh gosh, hey. Right. Because the problem is, you've got different parts, right? Every single part of this question is actually a new happening. And you have to look at that. So the first part would be to say, he's sliding down an inclined plane. Right. The second part will be he's going there over a horizontal plane. That is something different. Right, now he's hitting the parcel. So there you've got a collision. That's something new. And then he's swinging up, and that is something new. Right, so you've got 4 different parts of this question. And now the question is, which equation for which part, right? Because there's velocities all over, there's masses all over. It's difficult to know which one. And that is what we're now going to do on page 14. So if you look on page 14 on the left-hand side, we are going to see what should I look for in a question in order to decide which equation will be best to use. And the most important thing is this a closed system or not? What is a closed system? One with no external forces, right? No friction, no applied force, no external forces, closed system. Right. So the first thing you have to look for in every single part of the question is there friction or is there not friction? Right. So if there's no friction and no applied force, then you are in a closed system. And in a closed system, things are contained. In a closed system, no one is having a hand from outside and adding energy, right? There is no friction that is removing energy. So in a closed system, things stay conserved. It stays constant. If it's conserved, it's not lost, right? That means before and after you'll have the same amount. So if you look at a closed system, we have conservation of mechanical energy, and we also have conservation of momentum. Right, and the moment you're using with conservation, what will be the first step? The first step we'll see, if it's conserved, it stays constant, right? So conservation of mechanical energy means the mechanical energy before and after are equal. The same with momentum. The total momentum before and the total momentum after are equal. It's conserved. It doesn't change. Everyone happy? Now, if there's no friction, you can use conservation. Right. Now, when do I use the top one? When do I use the mechanical energy one? I use that whenever I've got something moving. Well, you have to have up and down because it's got an H in there, right? So when it's up and down, but it can be a pendulum, right? Something on a rope that's swinging, right? Pendulums. Free fall. Why can I use it with free fall? Because free fall's got only gravity. So it is a closed system. So something that I did with projectile motion, I used equations of motion, but I would have got the same answer if I've used mechanical energy. Now, also with inclined planes and curved planes. And now, sometimes this is the only way to do it. If I've got a pendulum, and that pendulum swings from there to there, they can tell me the height, right? and they can ask me, if it's starting from rest over there, what will be the velocity down there? Can you do that with an equation of motion? No, why not? It's not in a straight line, right? It's not in a straight line. So you may not do that with equations of motion. So for a pendulum, the only way to do that would be to work with energy principles, right? To work with mechanical energy. So for pendulums, I immediately go to this one, because this is most probably the best way to do it, right? Or the only way to do it. Free fall. If they say in a free fall question, use equations of motion, then you're stuck with equations of motion. But if they don't say it, you could have used this as well. Let's take an example. Typically, I'm telling you I've got a ball down here that I'm shooting up with, say, 12 meters per second. It's going up, 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 and I'm asking you, okay, let's say it starts from a height of 0.5 meters. It's going up, 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 starting from 0.5, and now it goes up to a maximum height, and they ask you, what is that maximum height? Now, what would you have done with projectile motion? Projectile motion, you chose a direction as positive. First thing, you would have said, let's choose up as positive. Now, I have an initial velocity down there of 12, and it is in the positive direction, 12 meters per second. Right. What is the final velocity up there? 0. So final equals 0. Right. What do I know about this? No gravity, no air friction. So you've got gravity, and gravity is working down. Right. So now it is negative 9,8 meters per second squared. And we're actually looking for height. So I'm looking for delta x or delta y. Right. If it's up and down, I make it a y, but it's not necessary. You may use x. Right. So we're back with equations of motion. I've got the a, which is the g. I am looking for delta y. What don't I have? Time. It's easier to say I don't have time, so choose one that don't have time in there. So I'm going to say, okay, let's say v final squared equals v initial squared plus 2g delta y. Final is 0. Initial was 12. Remember to square. Right. Plus 2 times minus 9,8 times delta y. Now I need someone who's quick on the calculator, because I haven't worked that out. First one to give me that answer. Come on. Three five. Okay, 7,35 meters. Right. Is that the answer to the question they asked? No, because I only calculated that part. Right. So if I want the maximum height, I will have to take the 7.35 and add 0.5. That would give 7.85 meters. That is the maximum height. Everyone happy with this? Old news. Now we're going to say, okay, there's only gravity working on this. So immediately I may say the mechanical energy down there is equal to the mechanical energy that it will have up at the top. Right. Mechanical energy, just EP plus EK. This side was for initial, that side was for final. Right. Give me an equation for potential energy. Yes, mgh plus half mv squared, all for initial. mgh plus half mv squared, all for final. Right. And what I can even do is I can even cancel out the m's. Eh? Right. Because it's not 0, I can divide every term with that. So over here, now remember what's in this one. In this one, I have to know that, remember, we're working with energies. And then for V and G, there is no sign. So now you may not put positives and negatives into G. In this equation, G is always just 9,8. We're working with energy. It doesn't have a direction, right? Just 9,8. What is the initial height? 0,5. Initial velocity, 12. Final, g is 9,8. We're looking for the final height, right? And what do you know about the velocity up there? 0. And then you can work out that final height. Did you check that? Happy? Right. And isn't this much easier, actually? You don't have to remember, oh, is G positive or negative? What is delta Y? Right? It's nice, huh? And something else. You have to choose from which height you're working with. In this one, I started off by saying the initial height is 0.5. Right. But you could have changed it. You could have said, okay, let's make that height 0. Okay? Then this would have been 0. But then you would have ended up with 7,35. Because then the final was also measured from there. Right. So just remember the initial and final is measured from the same height. So when I did it in blue, I measured from the ground. When I did it in red, I measured from the height from which it traveled. But then, to get the final height, the maximum height, I will still have to add the bottom part, because then it's 7,85 meters, and that is from the ground. Right. So what's nice in this one is you can choose your own reference point. And if they give the question with everything measured from the ground, work from the ground. Right? Don't go working from somewhere else if it's not necessary. Everyone happy? Is grade 10 coming back a little bit? Right, nice. Okay, so if there's only gravity, there's no external forces, you've got a closed system and you have conservation of mechanical energy. And when it's conserved, it stays constant, so you can say the initial is equal to the final. Right. But it's also true for conservation of momentum. Right, so when do I use conservation of momentum? Right, collisions and explosions, right? Any collision, any explosion, you don't even have to think about it. They may not include friction because then you can't do it. Right. So we work with a closed system. But here is the catch. What is the catch always when we work with momentum? Directions. Directions. Here you have to be very careful to put in plus and negative. If something bounced back and you don't put the negative in for the final velocity, then it will be wrong. Hey? You have to have bounce back. Right. So for closed system, you have conservations. And that's the easier one to do. Right. Now we get down to here. Sometimes it can also be elastic. A closed system is not necessarily elastic. It might be. And elastic means the total kinetic energy is conserved. Right. Now, our time is running on, so I'm going not to talk too much about this. We'll see if there's some time somewhere we can come back to this. Let's look at the right-hand side. On the right-hand side, now this you can do with or without friction. It doesn't matter. You can also do it for that one. We could have done the same thing we could have done with W net. That would have worked for this one as well. For this one, for W net, what is the only force working on this one? What's working on my ball as it's going up? Only gravity, right? So the net work is equal to change in kinetic, but the net work is only the work done by gravity, which is half mv final squared minus v initial squared. Right, work done by gravity, it's the whole gravitational force. Do I have the mass? No, so come on, just put 9,8 m in there. Times, we are looking for this traveling distance, delta x, right? Cos. Now, if I'm working with gravity, gravity is working downwards, and I'm moving upwards. So this should be 180, right? So I'm ending up with minus 9,8 m delta x. Okay, it's looking horrible. Let's see if it works out. Right. Equals half m. Okay, never mind. It will cancel out on the other side. Right. V final up there, 0. V down there, initial, 12, and remember squared. So that is minus 144. And then the m's will cancel out, and I will end up with a delta x of 7,35 meters. And then I say, okay, so that maximum height will be 7,35 plus the 0,5 below, and that will also give you some I for mine. So there's 3 different ways to do the same question. Right. And sometimes on the memos they forgot one of the options, and then you feel, oh, I'm wrong. Right. If there is no friction, then you may use conservation, but you may also use this. This is with or without. Right. Now say there is friction. May you use the left-hand side? No, the left-hand side is out. No friction, no left-hand side, right, if there's friction. So we have to go to the right-hand side. Now, on the right-hand side, we've actually just got 2. We've got the work energy principle, and we've got the impulse momentum principle. And then the work energy for non-conservatives, just a special way to do the W net one. So what is the difference between work energy principle and impulse principle? When do I use that one? When do I use that one? If you look at W net equals delta EK, what do we find in a W? A W has got a delta X. Right. So if they give you delta X, then I'll go with that one. It will be the easier one. But if you look at the impulse momentum, you remember that one, impulse momentum. Fortunately, you've just written exam, so he's fine. Huh? Right, impulse momentum. If you look at the impulse momentum, what do you have there? There you have delta T. Right, so if you read your question and they give you delta X and there's friction, friction tells you I've got to be on the right-hand side. Delta X tells you work energy principle. Right, but if they give you time, then this one will be easier. Right, you can always confuse them by using an equation of motion when they give you T to get delta X and then do the top one, but it will not be on their memo. Hey? Right. So if they give delta T, do this one. If they give delta X, do that one. Right. And then if there's no bottom corner, no angle, then you just switch that on for the non-conservative forces. Right. So there's not that many. So let's go and look at our question on the right-hand side. So we're on page 15. Now let's read slowly. The script of a new James Bond movie includes the following scenario. James Bond, 80 kilograms. Right, go and write it in. 80 kilograms. I don't want to read the passage. So he's 80 kilograms. Starts from rest. So V initial over there is 0. Skis down a 25-meter slope. What is the 25? It's the delta X over there. Down a slope, and the slope makes an angle down there of 38 degrees. And he experienced a frictional force of 10 newtons. Okay. Then at the bottom of the slope, now we're getting to the second part. At the bottom of his slope, he covers a horizontal plane, and now they give you 15 seconds. What's that? They give you a delta T. 15 seconds. And once again, he experiences a frictional force of 15 newtons. It brings him up to a parcel with a 1 kilogram, go and write it in, fixed to an elastic rope. He grabs the parcel. So what do we have there? Grabbing onto the parcel is a collision. Right. So over there we have a collision. And now he and the parcel all together swings up. Right. Now they say nothing about friction, so we can take friction as being ignored. Right. so there's no friction for that. Swings up, and now he comes up to there, and now he releases the parcel, breaks the window, escapes through the building. And to do that, he requires 5,4 times 10 to the 5 joule to break the window. And now the big question. You are the technical advisor to the producer. And you must determine if this scenario is at all possible. Okay. So what do you want to know? You actually want to know what is his velocity there at the end so that you can work out his kinetic energy. Right. Now, when you have different parts of a question, the most important thing to remember is the final velocity of that first part will be the initial velocity of the next part. Right. So you take this part and you work out the final velocity. That gives you the initial velocity for the second part. And then the final velocity for that part is the initial velocity with which that James Bond goes into the collision. Right. And then the final velocity of James Bond and parcel together will be the initial for the upswing. That's the important thing to remember. Now let's start and we look at every part of this four-part question. If we look at this first part, what's the most important thing there? Friction. Right, it's got friction. So go back to the equations. What am I supposed to do if I've got friction? I may not use a conservation. If there's friction, things are not conserved, right? I have to use one on the right-hand side. Okay. Now, in my question, what do they give you? They give you delta x. Right. So immediately, that tells you what should I do here? I should work with the work energy principle. The work energy principle. Right. And what am I trying to do? I'm trying to work out the final velocity of this part. Everyone happy? You'll have to do it soon. Okay. Now we're moving on to the second part. What is the most important information about the second part? Friction. Right? There's friction. So immediately I'm not allowed to use conservation. I have to go to the right-hand side. And what do they give you? Delta t. What does delta t give you? If it's delta t, then you're going to use the impulse momentum. So there I'm going to work with F net delta t equals delta p. Just what's very important with momentum? Directions. No? Directions. So choose a direction as positive, right? You've got a momentum. Okay, next one. We've got a collision. Immediately I see collisions, I'm going to work with what? Any collision, any explosions, conservation of momentum. Right. So for this part, I will say the total momentum before is equal to the total momentum afterwards. Right. And now I'm swinging up. Last part. I have got a pendulum. And whenever I've got a pendulum, what am I going to use? I'm to use conservation of mechanical energy. So for there, I'm going to show E mechanical down there is equal to E mechanical up there. And that gives me my final velocity up there. And then I'm going to work out the kinetic energy of James Bond and see if he's got enough to escape. Right. So it's over to you to do the questions. Right. So find out if he's going to make this. Is it going to work? Is it not going to work? Right. The angle that I use for gravity, it's moving down the slope, right? So this should be 90 minus the bottom angle of 38, right? So you're going to be working there with 90 minus 38. Right, important. If you start with a question, it's always good, even if they don't ask you, draw a force diagram to make it easier for yourself. So if we're looking at this part where it's moving over the ground to the right, what forces are acting on this one? Now, let's draw it quickly down there. You've got gravity working downwards, you've got the normal force working upwards, and what do you have? Friction to the left, which is very important because those two are going to cancel out. Remember, it's not going up, it's not going down. So together, those two should be 0. So what is the net force over here? It's actually that one. But remember, it is negative 15, right? The net force is negative 15. So if you forgot about direction, you put a 15 in there. James Bond would have speeded up, right? He's slowing down because the force is acting in the negative direction. And then delta x, he is moving, delta t. Whew. Okay, sorry about that one. Okay, and the time is 15 seconds. And then change in momentum is final minus initial. They've both got the m, and it's finus minus initial. Final minus initial. Right, mass 80. We're looking for the final one. It went in there with 17,19. And then if you do that, you should end up with 14,38 meters per second when he reaches point B, just before he grabs the parcel. Right, can I see how many of you got 14,38? Yeah, good. So now we are going into the collision. Right, and a collision is always a change in momentum. Now let me just write next to this one. Okay. The total momentum before is equal to the total momentum afterwards. So it's the momentum of James Bond and the momentum of the parcel, and afterwards is the momentum of James Bond plus parcel. Right, and this is for initial, and that is for final. Right, so this will be MV, and it is for James Bond before everything. And that is the parcel, MV parcel, before. And that is M plus M for James Bond and the parcel and the final velocity. So, James Bond, mass 80, and he was traveling at 14,38. The parcel is standing still, so it's got a zero momentum. Right? And afterwards, you've got James Bond plus parcel, and they're moving at the same velocity. And then you have to work out that velocity, and that is 14,20 meters per second. So that will be, let's call it number C. That is when they start swinging up. They start swinging up with 14,20. Everyone happy until this? Okay, now the last part. Now we're swinging up. It's a pendulum, so we are using mechanical energy. Right. Everyone finished here? Can I cover this one? Let's give a second for the guys who's writing. Let's go on. So now we are doing the swing. We with a pendulum, and with a pendulum it will be the mechanical energy down there will be equal to the mechanical energy up there, the final one. Mechanical is EP plus EK. This is for initial, that is for final. Potential, mgh, kinetic, half mv squared. Potential, mgh, kinetic, half mv squared. I'm just going to cancel out the m, they're all the same, so I can divide every single term with that. And then what do I have to remember about g? Plus or minus? No plus or minus is in here. So this is just, he's starting out from the horizon, so the height is 0. He's starting out with a velocity of 14,20. That's what we calculated at C. And now G 9,8, and it's going to a height of 5,2. That's what they told us in the question, 5,2. And now I want that final velocity at the end of the swing. And if you calculated that, it would have been more or less 9,99 meters per second. Remember, it might be a little bit different if you rounded off along the way or didn't round off along the way. Right. More or less 9,99. So that is the velocity of James Bond and the parcel up there. And now we're just quickly going to have what is the kinetic energy of James Bond up there. It's half mv squared. Half, James Bond is an 80 kilogram guy, and that is 9,99 squared, giving you 3992,00 joule. Will he make it? No. What do we need? What does he need? He needs 5,4 times 10 to the 5. Right. This is actually not enough. So, yeah, not enough. Right. Not enough. He will be banging his head against that window and he will not be breaking the glass. Right. So he won't be able to escape. But fortunately, it's just a film. They can have someone else breaking the glass. Huh? Special effects. Right. Right. Everyone happy with that? There's a lot more questions, but our time has run out a little bit. Did you learn anything new today? Yes. Right. So if you want to go back, okay, I'm glad you found that good. Remember to go back to page 10. Page 10 is your summary of the whole chapter. And then if you want to do one good example that covers all the methods, then you go to page 13, that washing machine one. Cover it up with the paper and redo it. So then you'll have a memo that you can look at. Right. And then you have to go back to page 14 as well and check all the equations.